worked in Portsmouth and in Seaside here. And she works on cosmology, structure, formation, and the application of various approximation schemes in these fields of science. She will officially begin her work here in January, but she has come for a week. She will stay until Friday. I encourage everyone to interact with her. And then I would like to introduce our speaker today. So this is Boud Roukema, who is a professor at Nicolaus Copernicus University in Poland, the physics department. He works on cosmology and astronomy. He works about him. He did his master's, his bachelor and PhD with others at Mount Stromlo Observatory in Australia. Then he did his postdocs in Paris, Institut d'Astrophysique, in Brighton, in Japan, in Tokyo, in Pune, in India, and then Observatoire de Paris-Meudon. And since 2002, he's been working in Poland. And he works on cosmology, Pan-European body simulation, merger history trees, also the cosmic topology observational methods, and now he's working on homogeneous cosmology and on the backcorrection problem. And I think this is the topic of today's seminar. So, please.
Okay, thanks. Okay, so that's all the introduction. So I will start with some easy slides. Okay, I know not everybody here is a relativist. There are some people who know much more relativity than I do. But some people are in topics like condensed matter physics. So the basic theme is you have probably heard, in fact it's something like, it's what's called Goebbels' method, that if you repeat something often enough, then it starts to become truth, or at least people feel it's truth. So in cosmology, people have heard that lambda CDM fits all the observations, that it's the general relativity interpretation of our observations. So people tend to think this is, in fact, correct. People like Mikowai and myself say that, in fact, the lambda CDM model is, in fact, not quite relativistic. Okay, let's start from simpler things. Okay, the universe in our physical model is space-time. So technically, it's a manifold, rozmaitość. So a four-dimensional manifold, a Lorentzian four-dimensional manifold, and this is the hypothesis that has been around for 1 century. And then the question is, in the context of the Einstein equation, what are the space-time manifolds which match the observations? So there are the observations, the analysis of observations first by Georges Lemaitre in 1927, and then 2 years later there was another guy called Hubble who had a better media team. He published these things on YouTube, so he got more publicity, and so we call this the Hubble expansion. Okay, thanks. Anyway, to match the observations, people wanted to apply the Einstein equation, but the real universe, as we know from today's observations, is inhomogeneous. We have clusters of galaxies, we have big voids, and in the 1920s and 30s, people said, well, let's just assume that the universe, well, let's split up space-time. Let us suppose that we have what we call comoving space. So we have a set of coordinates for all of space for one single time value. And then we have the time parameter, which has some linear range of values. And so that way we have a foliation of space-time. And then we look for what solutions we have for an expanding universe. So this is a rather simple family of solutions of the Einstein equations. And for roughly a century, people have applied these to observations. But to fit this to observations, the observations of the 1990s, so faint galaxy counts and gravitational lensing, and then what became popular was supernova of type 1a. Then people found that if we have this homogeneous model, we need this magic term lambda, so a cosmological constant. But this family of solutions does not take into account the fact that the real universe has voids and clusters and all sorts of complicated structures. So strictly speaking, this standard model is Newtonian for two reasons. Well, it turns out that this best fit homogeneous model has zero curvature. And so for many purposes, the calculations are Newtonian rather than relativist, although there is a sort of relativist motivation. We know that the real universe does have galaxies, and so the aim in homogeneous cosmology is to go one step further beyond the homogeneous models and to find a relativistic way to model this structure formation. And most of the debate is not closed, but we have many indications that when we take into account this structure formation, we have expansion and curvature evolving together, and then we don't need a lambda term, and we have a nice relativistic model of the universe. Okay, so today I will talk about just one of the approaches. Here I go back to the family of homogeneous solutions just to remind you of the intuitive tools for cosmology. Well, all of you know at least symbolically what a metric is. For the metric of the surface of the Earth or the two-sphere, okay, we can project a curved space onto a flat screen. And now in our flat intuition, we say, okay, something is wrong, that Antarctica looks like it's a huge annulus. And Australia is huge, and Europe is, well, Europe is rather small anyway. But here Australia is bigger than the United States. Madagascar is as big as Europe. Sorry? Angle preserving.
It's not just a projection, because the distance between different parallels is kept.
Well, in this direction, the metric is just dr. In this direction, we have a sine function to correct it. So mentally, you say, okay, first off, I have this flat intuition, and then you say, but this is just a coordinate system, just r and theta, and I have a formula, dr squared plus r squared d theta squared, or r squared, well, big R squared sine of little r on big R squared, and so I have a correction function. And so really, here, this is a circle of circumference 0, so you just mentally correct this. So this is what we have to do in cosmology. And it's a little bit tricky, but it can be done. Okay, the standard family of models. So in the 1980s, this was the standard model. So there are many observers which made sure that they agreed with the theorists. So they showed to very high significance that omega matter was 1 and the cosmological constant was 0. And in fact, even the Perlmutter team had conference proceedings where they showed that the first early results were definitely getting rid of this lambda thing. But later on they got more data, and they said within this family of homogeneous models, in fact, we converged on this. So this is fairly stable. Sure, okay. Sure, okay. So I'll show the equations a little bit later, but when we choose this co-moving coordinate system, all the expansion is in a scale factor A of t. When you put this in the Einstein equation, you get out two equations, and you can rewrite one of the equations as a balance between curvature, density, and the expansion rate. And so if you normalize by the expansion rate squared, then you get curvature and density balancing. or curvature density and a cosmological constant balancing, and the sum is 1. So these are these normalized, this is the normalized density, this is the normalized cosmological constant or dark energy, and then these two plus the normalized curvature add up to 1. So they're normalized by the expansion rate. And so these are both models with curvature is 0, and so that's why curvature is not listed here.
Or you can just say they're normalized by some critical density, which is defined as the density from which the global curvature disappears. And then this means this is total energy density of non-relativistic matter, total energy density of the parameter that is cosmological constant.
Sure, that's another way of saying it. But in this density, the main thing is the expansion rate squared, which is a function of time. Okay, so within this family of models, we have about 30% matter, which includes dark matter, and we have this mysterious dark energy. Okay, so, cosmologists in the second half of the 20th century and the last decade and a half are not stupid, so everybody does know that galaxies exist. So what have people done? They have said that, okay, we have perturbations, so we define a delta, the density in a particular region minus the average density, normalized by the average density. So if the amplitude of this is very small, then you do Taylor expansions, and so if this is 10 to the minus 5, then 10 to the minus 5 squared is 10 to the minus 10, and then 10 to the minus 15, and so on, so you quickly get convergence. And so we have what's called the linear theory of structure formation. So this is reasonable at early times, especially since we have the observations of the microwave background, promieniowanie tła. But, well, a typical galaxy has, well, this capital delta, this is something like a number of 200. This is from, well, it's a mix of linear theory and Newtonian theory. It's to do with the, if we model something contracting spherically, then we expect it to be something like 200 times the average background density. So the observational density of a galaxy today, depending on what scale you choose to do the averaging, is something like 1,000. So it's a number much bigger than 1.
This is the same delta?
This little delta
Yes.
is the same delta, yes.
Is this one?
Yes. Well, 1,000 is not a small perturbation.
It's just a breakdown
So-
of the perturbation.
Yeah, it's defined as the over-density. The density of a galaxy,
It's defined by the same formula?
Yes.
So it is 100?
1,000. Yes. Well, our galaxy, okay, us here, this Earth, this is not the average density. It's not a tiny perturbation.
So this is 10 to the minus 7, right?
Sure,
F delta at least.
sure. Yes, so obviously for a galaxy, this approximation, well, this is no longer true. So this is why people start calculations from the early universe and somehow have to calculate through to the present. So most often we use n-body simulations, and n-body simulations are highly non-linear, and so when they are non-linear, this means this approximation fails, and we're not quite sure how to do relativistic calculations in this situation.
This subscript here means that it has something to do with virial theorem.
Yes,
So what,
virialization.
so
the-
what is
well-
the relation with the virial theorem that we know from standard classical mechanics?
It's not any tight. This is, for example, from Lacey and Cole 1993, so
There must be some relation because someone
Well-
called it virial.
There
So
is,
what is
Sure.
the relation with virial?
That's such a
it's a density contrast at which after Hubble time you exchange your excess irrational potential energy for the random motions of, just intervalize your potential. So this is realization threshold. It's exactly Birkhoff Theorem for the cosmic density fluctuations. So it's a balance of the kinetic and potential energy.
well,
Well,
there are different sorts of calculations. In general, this is not related directly to the virial conjecture I'm not sure how sure you should really call it a theorem. Some people call it theorems.
Okay, the thing is that we believe that at some point these structures, for
Co-
example, this pattern defender, in that case they have to satisfy the Virial theorem, and then there must be a relation between kinetic and potential energy, and this happens at a certain threshold for the density.
Yep.
So it is related to Virial theorem.
Well, it's related, but in principle it's related. In practice, it's not always related directly.
Well, you're skeptic, I think it's your theorem, you have right to be skeptical.
Well, I agree. This is not. It's not a hard science. There's lots of approximations which we have to do. That's how cosmology has advanced since the 1960s. Well, probably through all of the 20th century. Okay, voids. Typical underdensities of voids. On scales of something like 10 megaparsecs or 20 megaparsecs, this goes down to minus 0.9, so 90% underdense. So, okay, this is not, in amplitude, it's not as big as 1000, but if you want a Taylor expansion to converge, when you have something close, something like 0.9, then if your coefficients are not small enough, then you won't converge. Because 0.9 and 0.9 squared and 0.9 cubed, and with something like, say, 10 times and then 100 times, well, your risk of converging is, your chance of converging is low. Okay, so the general hypothesis is that at small scales, this family of homogeneous solutions, okay, in cosmology, 3 gigaparsecs is a small scale, and at recent epochs, so redshift less than 3, this is when we expect things to go bad, and this is when we expect the standard model to not quite work.
How can you claim that 3 gigaparsec is smaller than cosmology? It's comparable to the Hubble rate, so it's actually the observable universe scale, so it's the largest that we consider.
Well, Hubble radiuses depend, if you mean C on H0, well, the co-moving radial distance to the matter epoch horizon is 10h to the minus 1 gigaparsecs. So it's only 1/3 of this.
Yes, so this is not small. I don't know why you're saying it's smaller than cosmology.
Well, this is small because I want to be conservative and I want to include the epoch of galaxy formation. Well,
So EDS should fail at what is smaller than
at length scales.
length scale?
Length scales, which are much less than 3h to the minus 1 gigaparsecs.
Okay. And this number on the right hand side for the non-experts, how much?
Little h, it's close to 1.
Yes.
This is the normalized Hubble constant, so 0.7. Okay, so I didn't show a detailed diagram for that, but if you go to our 2013 paper, we show that, okay, if you interpret the observations within this homogeneous model, then you are ignoring the fact that at low redshifts there's structure formation. In that case, the cosmological constant in terms of these omegas is not a constant. And so, in fact, it only becomes significantly non-zero at low redshifts. So at redshift of, let's say, 6 or 10, it's much less than something like 1% or even less. Well, at z equals 1000, the omega lambda is about 10 to the minus 9. So when people say, okay, we detect, we confirm lambda CDM in the microwave background, well, there is no detection of omega lambda equals 10 to the minus 9 in the cosmic microwave background. So when people say that we have lambda CDM from the microwave background, what they mean is that they project lots of things across the past light cone, and when you put all these things together, then the interpretation is that we must have omega lambda this certain value at the present. But in fact, this is the present value of omega lambda, it's not the value at the microwave background. So really, this omega lambda here, this grows from almost something like 0 to close to something like 40 or 50% at the present, in the same way that if we define an inhomogeneous parameter, so the fraction of matter in collapsed dark matter halos, I call it FVIR, so the fraction of virialization. If we look at how this evolves from, let's say, redshift of 10 to the present, it goes from almost 0 to something like 40 or 50% at the present. So the omega lambda and the virialization fraction grow from almost nothing to something like half of the, well, something like a fraction of half at the present. So they really match quite closely. So this is a strong qualitative indication that we should take structure formation into account.
Fraction of the mass and relativistic matter enclosed in the virialized region.
Fraction of non-relativistic matter, yes.
You know the volume of mass at the same time as the volume of the non-virialized regions. Is this half of perhaps objects are like 1% of the space?
Sure. And, well, this is a very strong argument of why we need to take inhomogeneity into account, because the almost empty volume dominates. And an empty volume is, if we go to the Milne model, well, this is getting a bit too specialist for non-cosmologists. This has negative curvature. Yep. Okay, so I want to speed up, well, I guess given this audience, I don't want to go too much into details, but okay, some equations. So this is the Einstein equation. If we want to allow, sorry?
Combination of letters.
Okay, sorry. Friedman, Lemaitre, Robertson, Walker. So this is the family of homogeneous models. Then one element of this family of models is the lambda CDM model. So lambda, cold, dark matter. Okay. Thank you for the question. Okay, if we allow a cosmological constant, then this is where we can put it in the Einstein equation. So curvature of space-time equals density and pressure, if we want pressure. The standard model is dust, so we have pressure is 0. So the stress energy tensor just comes from the 4 vectors, so the tensor product. Okay, so the standard approach is to ignore inhomogeneous curvature, ignore evolution of the average curvature, and we ignore structure formation. Okay, so
People assume Birkhoff Theorem's hold that is the question of Centrum Averaging in GR, which is still not well defined, but it's not ignored. It just say that the effect is natural. You can maybe show it's different, but I think it's not ignored like because this would suggest that ignorance of our part.
well, for people who know English well enough, this is I guess, a religious illusion. In cosmology, lots of people invoke Birkhoff Theorem, but you'll notice that almost nobody cites it because nobody checks what it actually says. Birkhoff Theorem requires asymptotically flat conditions. In other words, the easiest way to do this is to have an empty universe, and in cosmology, nobody really wants an empty universe. So Birkhoff Theorem for modern cosmology is generally not very applicable. Well, I would say that people who want to apply it should actually quote the reference and then explain that the conditions of the theorem are satisfied. Because you have a theorem is if A, then B. If A is not satisfied, then you can't apply the theorem. Okay.
Aren't there solutions that violate Birkhoff theorem, that that's very good symmetry?
Well, the standard model. Well, it violates the conditions. It's not empty.
So it's not empty, asymptotically it's not flat.
No, because it's expanding. This flatness is in the 4-dimensional sense, space-time sense.
On supervising scale it is, but on supervising scale it is. This is the result of the structure.
It's not flat for sure.
Okay, so this is from the 2DF galaxy redshift survey. So this is an example of an overdense region. This is an underdense region. Okay, so the general approach of scalar averaging, that sometimes people call the Borchardt approach or the Borchardt equations, is that instead of having a single global average, we take averages in domains. So here this could be plus for an overdense domain, minus for an underdense domain. So in fact we expect that this will tend to have a positive curvature, spatial curvature. This will tend to have a negative spatial curvature. And so the idea is to do these separately and then see what you get together. Okay, so this is the averaged Ray-Choudhury equation. So it's one of the equations you get out from putting the co-moving coordinate system into the Einstein equation. Okay, I've put the reference here from the what we call the relativistic Zeldovich approximation paper 2. Okay, so what do we have here? The little a, this is the scale factor I've talked about, but the d means this is for some particular domain, so for some spatial region. This is the second time derivative, so informally you could say that this is the acceleration. So it depends on the density. So this little I means the initial domain. So these are constants. This evolves with time. So if we ignore this QD for the moment, then this is one of the standard cosmological equations for the homogeneous universe. When we apply this for a Lagrangian domain, so defining a domain defined by the particles, then there is this extra term which we call the kinematical back reaction. So this is, from a Newtonian point of view, a statistic. Well, I will show you a more detailed definition in a moment, but it is a statistic of the peculiar velocity field. Or another way of thinking of it, peculiar velocity, the gradient of the peculiar velocity field. So more informally, it has information about how particles are moving in an inhomogeneous way. So it has these statistics contained in this. Sure, yes, okay, this means, yes. The co-moving, I didn't give you a definition of the co-moving reference frame, but it's a choice of coordinates in which the universe is static. So all the expansion is in this global factor AFT. When we go to domain-wise expansion, then it's in AD of t. So that means also for what we call peculiar velocities, because the universe is static, once we have got rid of this, then there's still some velocity, and so velocity is a local thing. In any case, in general relativity, a velocity only has meaning locally. If you want to have a velocity over there, you have to transport it in some way here before you can talk about any relationship. Okay, so here is one way of defining the kinematical back reaction. So these are invariants.
Why is it called back reaction? What is reacting back on what?
It's a bad choice of terminology. Okay, but it's historical, and now it's become standard to say this. Well,
in a more logical context, when you have a particle radiating and then the back reaction of radiation, so there must be some connection with
well, the connection is that the idea is that first we have this homogeneous, if you like, real physical thing, and then we have this extra inhomogeneous thing, and this
so
back.
Different regions expand at different
Yeah, and then this back reacts, and so the average thing also becomes different. And so then the
That the global expansion somehow acts on the small scale expansion and contraction and motions of particles, but then these small scale average motions also have some back reaction on the zero mode or on the large scale expansion of the particle.
Yep.
There is a homogeneous Hubble background. On top of that, there's complicated physics. This Hubble expansion affects this complicated local physics, but also there is some influence from local physics into the large-scale expansion. And this is what this is all about.
Yep. But again, the word is confusing and probably
So
yeah.
in this equation that you have for the acceleration,
Yep.
is there a term that is responsible for back reaction? So it's not included in
Well, this is the kinematical back reaction. So instead of just an intuitive word, this is a formal definition. So these are invariants of the peculiar velocity gradient. So this is a tensor. Well, from a relativistic point of view, this is the extrinsic curvature tensor. From yes, yes. Well, it's if you think of it as a matrix, then it's 3 by 3. So from a Newtonian intuition point of view, it's the gradient of the peculiar velocities. So these are statistics. This is a first order statistic. This is a second order statistic. If you like, this is more or less the average peculiar expansion. So when you subtract off the smooth Hubble expansion, this is the extra expansion. Then this is from the, well, when you multiply the expansion in different directions, so statistics of these. So when you put this in here, you get the effective average expansion, well, acceleration of this particular domain. Well, the particular work that I'm going to show in the remaining 20 minutes is a numerical way of calculating this. And the idea is to calculate this in individual domains, calculate these, in fact, we calculate these initially. Well, in fact, this will be clearer when I show you the next few formula. We calculate these statistics in the same way that is done for standard n-body simulations. We generate these. And then there are some nice formula which say how this kinematical back reaction should evolve with time. And then we do this for all the individual domains, add this up, and so we have all the accelerations, so we have all the evolution of the individual scale factors. We add them up, and so we get an overall volume evolution.
You want to find its definition to the solar system?
No, it doesn't make sense. This is on a big scale.
Since you have definition which involves velocities, then what happens if you apply it to the solar system? Get some number.
There's no velocity gradient in the solar system because there's circular motions. So you have potential flow, pure potential flow, you have velocity gradient, right?
No,
So
Well,
you have to be on the info flow.
there's the question, we have approximations on different scales. On the cosmological scales, we don't have anything bigger in which we can embed things. The solar system, we can think of as embedded in a larger scale average effective model.
Yes, but the definition that you wrote here does not tell anything about this large scale. It says about the velocities. Right? You have
Well,
velocity.
it's the velocity of a smooth fluid flow.
Could not be localized to, as it is in the solar system, what planets move, not be smooth.
Yes, yes. Okay, so here's the more detailed definitions of the invariance. So Vij, so the components of the velocity of this fluid and the partial derivatives, so the jth partial derivatives, first, second, and third. Okay, and in fact for this one, my new paper has the correct formula for average square values of this, because in the Buchert 2000 paper the formula is wrong. It says after a lengthy calculation you get such and such, but in fact it's wrong. So the new paper has the correct value. Okay, so this is from two of the different Buchert et al. Papers. So this applies both in the Newtonian and GR cases. So what is this? So this is how this kinematical back reaction term evolves as a function of time. Okay, what are all these things here? Okay, these gammas are just shorthand for what is defined here. Here you see the invariance. So these are the invariants I showed you a moment ago. So these various statistics, well, here this is at a particular point. So when you take the average of these, you take the average at the initial time. So these average statistics, first, second, and third order statistics, So we have the initial conditions in a particular domain. This psi is the linear theory perturbation growth rate. Well, in the papers there's a more formal definition, but effectively it's that. So in other words, this is, well, it's also normalized and the 0 point is removed. Sorry? The growing mode, yes. Yep. The 0 point is removed and it's normalized. So if we have, so this is against a reference model. So in the papers it says background model. Yep.
Do you use any of the Buchert equations to write the relation from the kinematical back reaction, or just rearranging the different?
Well, it depends how you define the Buchert equations. This is one of the normally called.
And also the energy constraints.
Well, this is in this paper, the RZA2. So whether you want to call it a Buchert equation or not, that's up to you.
No,
That's just a name.
Okay, so which information do you use to write that relation from the kinematical back reaction? I mean, do you use any of the equations, or?
This is from the Jacobian of how space is stretching in different ways. So, well, it's from the Buchert papers. The shear tensor is related. Well, you have to have different combinations of these if you want to think in terms of shear and viscosity, vorticity.
So is the growth rate the same as expansion rate?
No, this is the growth rate of perturbations. So after subtracting off the smooth expansion, this is how a density perturbation grows. It's how the this delta grows as a function of time.
Does it depend on space and time?
It depends on time. Well, this is to apply this in practice, we choose a reference model. The papers use the term background model, but we've realized that this is confusing, so I'll say reference model. And so the reference model we use is the Einstein de Sitter model. And in that case, it turns out that the value of delta of t turns out to be the same as A of t. So, well, if we draw a picture, if this is the average density, well, if I put 0, so let's say we have a density fluctuation like this. So if the scale factor grows by a factor of 2, then the idea is that this gets a factor of 2 times bigger. In fact, this is inconsistent because it needs to contract also. But
that's not the same as psi.
not quite, because psi is this minus the value at some initial time and divided by the value at the initial time. So it's just normalized and the 0 point is removed. But it's more or less just this standard growth rate. Well, t on t0 to the 2/3. It's not proportional to time. Sure. Okay, so I've even written it. It's written here. So if psi is from the reference model, it's the linear growth rate. Well, it should say that it's 0 point and 0 point removed and normalized. It's not said here. Okay, so if we have these.
So
Well, okay.
this is an important formula.
Yes, yes.
What is needed to derive this formula? Einstein equations?
The Einstein equation.
At some point?
The assumption, well, this, in the relativistic case, this is done with Cartan coframes to follow density perturbations very locally. And then,
You can in fact derive this equation without Buchert equations.
yes, you can derive it either in the Newtonian case or in the relativistic case.
And they are the same in both cases?
The structure of the formula,
But this formula
Yes. Well, the structure of the formula is the same, but they are different in the sense that in one case these are defined in a Newtonian sense, the initial invariance, and in the other case they're defined in the relativistic sense.
But the formulas that you gave before looked at the universal. They do not depend on whether you take Newtonian or Einstein. These formulas, yeah, go. The definitions of these invariants. The definitions of these invariants
Yes.
involve only the distributions of
Sure.
the oscillations.
Well, here I've written down the Newtonian definition, so if you want to write...
This is the Newtonian case.
Well, yes.
And
But-
what would be and in the Einstein case, these formulas are different.
They are different, but at an early time, the differences are very small. So, okay, yes, but
The formulas look different in the Einsteinian case.
in principle, yes. But the limit is the same.
But you know that in the Newtonian case, the kinematic reaction does not exist. So it's no result.
Well, I think will confuse people if you say this. The kinematical reaction in a domain, Thomas Buchert is totally clear that he agrees that it's non-zero. It does not disappear. And the Newtonian, he agrees that it does not disappear. He's an early draft of his, well, we'll get into this later, I think. His early draft was not worded so carefully. His later draft, the one that got submitted, was more careful. Okay, so, well, I'm fairly sure I'm the first person to say this. Anyway, my description of the standard model is that we have verbal averaging. So there's this, the cosmological principle. It's a principle, so it sounds very important, but in fact it's verbal averaging. So here, the Buchert approach is mathematical averaging. So you add up the volume evolution or scale factor evolution in the individual domains, normalize by the number of domains. In this case, they're all normalized by 1, but you need the sum of them. And this gives you an overall expansion.
Why did you put this again? It's not Hodder averaging in the verbal, you choose what your domain size, what is the domain, right? Because there's always the user parameter.
Sure, this is what has to be discussed. Sure, but it's still mathematical instead of verbal. And there's no more applying a theorem which is inapplicable. Okay, so QZA, because this Zeldovich approximation is both in the Newtonian case and relativistic case, I propose just to say it's the QZA model. So it's the model it's this formula I showed you for the kinematical back reaction. So we set lambda to 0. This is what I've been saying. We assume silent virialization, so we assume that each of the domains evolves in a Lagrangian way.
Is there any physical reason why you take the third power and then you take the third root in averaging?
Yes, because the scale factor is in one direction.
Yes.
So we have x, y, and z, so it's cubed. Yes. So convert between linear and volume.
This assumes possible anxiety of expansion. Because the classical model it calls the homogeneous and isotropic expansion.
Sure.
So you allow for non-isotropic.
Well, in fact, this little AD, the little AD is defined as, on the domain d mu in a measure theory sense of the volume, and this to 1/3. So
To extract the measure of scale in meters from the volume. In order to do it, take the third.
yes, yep.
But the domains are still expanding isotropically. Each domain separately expands because you only have one parameter per domain, not a vector, right?
The domains will expand according to this equation. This is an ordinary differential equation.
But 80 is just a number. It's not 3 vectors, it's just a number. So you assume the expansion in all directions between domains is the same. Just all domains
No.
expand
No. It's not isotropic. It evolves according to this equation. The anisotropy is in this, and in these.
Right, but AD is just going to get one number that you multiply the metric values, right? So you're going to stretch the metric in each direction by the same factor. So it's like isotropic.
Well, if you want to imagine it that, interpret it that way, okay, you can. But mathematically, it includes this statistical information which is extremely anisotropic. Well, it depends if the initial conditions are isotropic or not.
Yeah, but you collapse it to one number, which means you average over three directions over the domain, right?
One clarifying question, is your reference frame isotropic?
Yes, in this case, in this particular calculation. The reference model is Einstein de Sitter. Okay, so we evolve these. So it's an ordinary differential equation. So this is in the inhomog package. And we will tend to expect that until we get shell crossing, so until we get virialization, this model should not have any problems. In the domains which collapse, then you cannot keep evolving the equation because you get to zero, and mathematically the equation will go to minus infinity, or if you don't hit it exactly, you may go to negative volumes, which doesn't make sense. And the assumption built into this model is no shell crossing, so it should only work until shell crossing. So in this case, what we should expect is that this overall average expansion should match the Einstein de Sitter background expansion. And this is one example. So here, this is just for one domain. Well, in fact, if we assume we have a global domain and divide it into two subdomains, one underdense and expanding, one overdense and contracting. So this is each of the two domains normalized by the Einstein de Sitter scale factor. So this is the collapsing domain. This is the expanding domain. So here we have set these two higher order statistics to zero values, and this is starts at 0.005. And so you see, this is a very fast numerical way to calculate how the overdense domain collapses, the underdense domain expands, and when we average these volumes, so these ADs we do to the power of 3 and then add them up and then take the cube root. The overall effective scale factor normalized by this reference model is extremely close to 1 in this numerical calculation. So this is before the actual collapse happens. Okay, then we have to decide what to do at virialization. So here, since we don't have so much time, I will just speed up and jump to this line. So for these calculations, I assumed, well, it's really our group, although it's just my name on the paper. Anyway, that's another issue. Okay, the standard approach in cosmology, so this has been for 20 years, is that when something has normalized, we assume something called stable clustering. So this is what Peebles proposed in the 1980s, that there is a fixed density in proper coordinates, so in the local system of coordinates, so without any expansion factor. And so this is this famous, well, in fact, this is a value of about 180, well, 180 to the power of, well, the cube root. You work out the expansion factor at the time of collapse, and the overdensity at the time of collapse should be something like a factor of 180 if you have a reference model which is the Einstein de Sitter model. And so instead of having this scale factor go to minus infinity or to some negative value, we stabilize it at some high overdensity. So it's at some fixed scale factor. Okay, so now there is a question of interpretations. Okay, is this really relativistic? Well, it doesn't really follow the standard stress energy tensor, but the Einstein equation is something different. So in principle, you should be able to find out some effective model where you modify the stress energy tensor to model this stabilization, this virialization. This is not done in this particular paper I'm presenting. In this paper, we take the standard observational cosmology, well, you could say observational / slightly theoretical approach. We just stabilize the object. Okay, now the question, is this Newtonian? Well, it's not quite Newtonian because we're not going to get the background scale factor because we no longer have the balance between the contracting and expanding regions. Okay, what do we want from the observational point of view? Okay, here we have cosmological time. So the present age of the universe is about, well, 13.8 gigayears is the standard value. If we take observational values from micro-lensing in the bulge of our galaxy, then in fact we get about 14.7 gigayears. But cosmologists, when we do Bayesian calculations, we choose, well, it's not me in these papers, so I won't say we, but the Bayesian calculations exclude the values which cosmologists don't like. So the 14.7 gigayear values are excluded, so this avoids things, well, Bayesian calculations are not perfectly objective, is another way of saying it. Anyway, something like this is a reasonable, somewhere around here is a reasonable value. This is the overall effective scale factor. Okay, these pluses, red pluses, I'm taking as a proxy for the observations. We know that lambda CDM is like a fitting function. If we draw some random points and we draw a line through them and then we say, oh, it doesn't quite fit these points, and so we take a second line like this or we add some curvature, we know that this more or less fits the observations. So these pluses are more or less what we need to fit. Okay, these are normalized to 1 at the present. So we need a scale factor evolution which more or less matches these pluses. At early times, we want to match this standard model in order to match the observations. So we take an Einstein de Sitter model, so with no lambda at early times, so we have this blue line. So as you can see here, there is almost, by eye, you cannot distinguish the Einstein de Sitter from the dark energy model at early times, but at late times, we do not have enough expansion. So the missing expansion is about 16%. When you see these pie diagrams or popular talks on cosmology, people will say, well, we are dominated by dark energy. It's 70% of all the energy, mass energy density of the universe, so it's a huge problem. In terms of expansion, it's only a 15% problem. So it depends in which way you present it to decide whether it's a big problem or whether it's a small problem. From the point of view of expansion, we need about 15% extra, 15 or 16% extra expansion by the present. The slope at any time, well, slope, a normalized slope, is what we call the Hubble parameter. So the Hubble constant at the present is roughly the slope here, so this blue value. If we take this Einstein de Sitter model and evolve all the way until we get an expansion factor of 1, then we would get this pink value. If we evolve just to 13.8 gigayears, then we would get this yellow value. So the Hubble constant, the slope would be a little bit too weak. So we will not quite get the correct Hubble factor. So instead of 70 kilometers per second per megaparsec, in fact you can see these numbers, we would get this yellow value, so roughly 50 kilometers per second per megaparsec. So
what is driving the expansion if there is no dark energy?
Well, inhomogeneous expansion. So this kinematical backreaction term. Well, this is the question. Do we get the extra expansion from the inhomogeneous expansion? And so with these calculations that I've shown you, okay, the first part is the same as before, but we have added the assumption of stable clustering. So when things virialize, we assume that they are stable. We no longer cancel between the contracting regions and the expanding regions. In a simplified calculation, so if you look at the black line, for example, so this is the black line up to here is what I showed you before, is we have an one expanding domain, one contracting domain. Until virialization, the effective overall expansion normalized by the, divided by the Einstein-de Sitter expansion is 1. So there's no difference. After virialization, the contracting domain can no longer contract further because it has a volume of essentially 0, and so the expanding domain dominates. And so the average is extra expansion. So if this approach is right, the dark energy is the no longer, or it's it's the lack of compensation for virialized regions. Until here we have expansion and contraction cancelling, and here we no longer have any more contraction because there is no more space to contract out of. And so now the expansion dominates. I'll just...
Some kind of a local expansion.
Well, this is averaging everything, adding it up. Okay, here are the software details. Sorry.
Always local expansion.
Yes, yes. Adding them up and dividing by the number. Yep. Well, when Wojtek comes back later this afternoon, if anybody's interested in discussing, you should join us, because he is the person who should most be interested in this page. The most important thing is that in today's epoch, software should all be free licensed and publicly available. Publicly available is not enough. You need to have a free license to allow people to understand it, to allow people to modify it, to allow people to give it to other people. Each of the components of this is for the initial conditions. Each of these are free license, they are available. This is what Wojtek Hellwing is a specialist on DTFE. This is for calculating the statistics of the velocity gradients, or the extrinsic curvature tensor. This is done by me and Jan Ostrowski. So this is for the evolution of the Q. So more or less it's integrating these ordinary differential equations. It also has some other things which are more complicated, which are in the library part of this. Ramses is a very widely used, well-tested n-body simulation program. So this is used as a front end to, well, first we generate the initial conditions, then we use Ramses to read in the initial conditions, calculate the statistics, and then call inhomog to evolve the individual domains and then take all the averages. And this is within the context. Several of these, in fact, so far, MP Graphic and Inhomog are both in the Debian Astro system. So this is a wide community, there's a wide community checking process. Okay, results. Okay, so as a function of time, so we have to choose a particular domain size in which we choose all these domains. So it could be 4 megaparsecs or 2 or 1. Depending on the scale we choose, okay, if we go to a high scale, a big enough scale, then, okay, these dots are the Einstein-de Sitter model, the pluses are the lambda CDM proxy. So as you see, at early times they are the same, at late times they are different. Well, if we choose something like a 2 megaparsec scale for the individual domains, then we get this extra expansion. An important question is how sensitive this is numerically to different scales. These different scales here, well, this is the scale of particle resolution. This is the scale of calculating these average velocity gradients. This is the size of the domain, and this is the whole box. These are all 3 torus simulations, because this is the standard in n-body simulations. If we vary these ratios, you see the pink line or purple, well, okay, purple line is always 2 megaparsecs. This generally is something which stays close to the lambda CDM proxy. Here we now have some of the bigger scales. You see the bigger scales get close to the Einstein-de Sitter model, so we do not have so much virialization. So we don't have any non-cancellation of virialization and expansion. Okay, I'm getting over time, so I'll just speed up. These are median values of this kinematical back reaction term, okay, normalized by the expansion rate, so it's like the omega matter or omega lambda. These are just a few %. So the kinematical back reaction term is not huge, but it is not tiny. So you can see it's significant enough to, compared to, we have precision cosmology, where 1% is considered to be high accuracy or precision. Well, accuracy is more important than precision. In that case, 4% at early times, in fact, does have an effect. If we go to the average curvature, and you have to, it's very important that this is not the evolution of homogeneous curvature, it is the evolution of average curvature, which is not the same thing. And so this gives a very big effect. So if we take the purple, so roughly 2 megaparsecs, at quite early times, we get an omega of average spatial curvature of something like 2. So this is very big. This has not yet been tested. Well, people try to test it, but the error bars are huge for average curvature. This is the virialization fractions with the 2 megaparsec scales. So depending on, okay, if you choose some particular time, this is how much the virialization fractions relate to the effective expansion. So, for example, if we take an early time 4 gigayears, so this is many different realizations of these initial conditions. So, depending on whether you have less matter which is collapsed and virialized or you have more, then you either have a little bit less expansion or you have a bit more expansion. So this is self-consistent. And this is also a clue to observational tests. Okay, I'll go to the conclusion. So, at least at this level of numerical calculation, if we have the Einstein de Sitter initial conditions, so we match them to the lambda CDM observational proxy. So in this sense, they are matched to observations at the microwave background epoch, so Z equals 1000. We evolve according to this formula which works in the relativistic and Newtonian cases, based on the statistics of the initial peculiar velocity field or the initial extrinsic curvature tensor. If we have the simplified calculation, just 2 domains without virialization, then we find almost no difference from the standard model. If we allow virialization and we make this uncontroversial assumption of stable clustering, then the expansion is no longer cancelled by the contraction, and we get an effective extra expansion. So to get something which is more or less observationally realistic, so 16% more than the Einstein de Sitter model at 13.8 gigayears, we need this averaging scale to be something like 2.5 megaparsecs. Now this scale is the scale for nonlinear structure formation that has been used in statistics for probably 30 years, since before I started in cosmology. So there is a statistic that we call the 2-point correlation function for galaxies. Typically people say 5 h to the minus 1 megaparsecs or 10 h to the minus 1 parsecs. So it's a factor of 2 or 3 smaller than this, but a factor of 3 in cosmology is not much. So this is realistic as a nonlinear, so a typical nonlinear scale. So if we do this, dark energy. So if we take the expansion using this formula of spatial expansion on the nonlinear, if you like, roughly speaking, the biggest nonlinear scale today, then we find that the effective expansion matches the observations without needing a lambda term. Okay, all the details are in this. So this is officially accepted and so in press for astronomy and astrophysics. So I am here this afternoon. Mikaway has to leave at 3:30. Wojtek will be back here at about 2 o'clock, so for anyone who's interested in discussing, I'm happy to discuss more. But at least at first order, this seems like we have a good challenge for getting rid of dark energy by a very simple, very conservative calculation. So, discussion. Yep.
The initial data is the information about all the galaxies that we observe, right? What is in all these numerical
Okay.
simulations, you have an input from the table of all galaxies.
No. In this case, the initial conditions are standard initial conditions used for n-body simulations. So this is a widely used initial conditions generator. So it's from what we call the power spectrum. So statistics of the Fourier analysis of these deltas in three-dimensional flat space.
No, but that means distribution of galaxies.
Well, it's not real. I don't accept to use the word galaxies because a galaxy is highly nonlinear.
But what is wrong? You have
This is at an early time, so in fact it's roughly Z is, let's say, 100. So that, well, this A is 0.01 roughly. So these are small perturbations. These are perturbations of something like 1%, depending on which scale. At different scales, there are different sign functions. And these are realized in terms of a particle distribution.
So no place you use the observed distribution of galaxies in the universe.
This does not use the observed distribution of galaxies, correct. It's an assumption which is considered to be consistent.
The question is why not? We have knowledge of that time that we know all the galaxies, and we could use observed galaxies to at the starting point to define delta.
If we are here, the observations go backwards in time.
Yes.
So here we have galaxies, here we have quasars, here we have the reionization epoch, here we have just statistical fluctuations. We have delta T on T. So on a 10 gigaparsec scale, we don't really have galaxies. But the main thing is that from galaxies here, we have to interpret going backwards. Well, we want to start the calculation at an early time. So we want galaxies evolved backwards in time.
But
So,
we know galaxies that are early in time because we
But-
can see galaxies which have a big Z factor.
sure, but we have very incomplete observations. If we are here and this is 10 h to the minus 1 gigaparsecs, on this scale we have small narrow cones like this.
So what is
In the next 20 years, well,
your assumption about initial conditions better?
well, in fact, these simulations are on a small scale, but well, I will not say that my assumption is necessarily better, but this assumption is the standard assumption. So we make many realizations. Well, if we want a statistical statement, then you need many realizations. And so if we take each of our particular galaxy observations, for galaxy observations, we have radial velocities, we don't have tangential velocities. So that's just one example of a reason why observations are not enough.
A little bit different question. When you describe the process of getting maybe the right model, you said something that your cells or domains at some point stop compressing, they become uncompressible. So which scales we are talking about, and physically what that would mean? What are these uncompressible cells?
They virialize. They virialize. Particles go like this, and with the virial theorem,
Physically they form a black hole, so
ah,
the galaxy which is no longer contracting. What is it?
well,
Why the matter suddenly becomes uncompressible?
because, well, if we assume that on the large scale there is zero average vorticity and so on the small scale things will have a little bit of angular momentum. And so many particles will be moving around. It takes a lot of processes before you can get them to form galaxies, before you can get them to form stars or black holes. So then you need to go on to baryonic physics. You need to lose energy, have radiation, so that. Well, this is at a 2.5 megaparsec scale. Well, at this scale there are no. Well, this means that on a 2.5 megaparsec scale, well, this is what George Ellis calls finite infinity. You consider that this is essentially a statistically stabilized region, and you don't know what happens outside of it. And so, but within this, things are moving around. To form stars, the particles need to slow down so that the hydrogen can fuse. And to form a black hole, we have people like Agnieszka Janiuk and Bożena Czerne. They know you need a lot of work to get rid of angular momentum before you can have an accretion disk and feed things in and then have jets and feed a supermassive black hole. Yes. Well, but maybe a link to this. One reason why it's good to use something like Ramses, which is a standard n-body simulation package, is that this includes all of these recipes. So there was a Ramses workshop 2 months ago, and there people try to include all these processes of gas cooling. They form stars. You have black holes forming, so you have AGNs, and the idea is to have simulations that you can statistically compare to real observations through telescopes. So when we put everything together, in that case, it's obviously an oversimplification to say that this is really just a black box stabilized.
Okay, any more questions? Oh, if there are, then just thanks again.
Okay, thank you everyone.